Aloha BIOCHEM. In this second lecture on Chapter 5, we discuss oxidation and reduction. So this time we cover section 5.4 on oxidation and reduction. Oxidation-reduction reactions, also called redox reactions for short, are electron transfer reactions. In Chapter 9, we'll discuss proton transfer reactions, which are acid-base reactions, but in this chapter we touch on redox reactions. The author defines them as follows. A redox reaction involves the transfer of electrons from one element to another. What happens is one element loses electrons, another element gains those electrons. The one that loses them is oxidized, and the one that gains them is reduced. A redox reaction can be illustrated by the following example. Here, zinc metal reacts with aqueous copper 2 nitrate to form copper metal and aqueous zinc nitrate. Here's the chemical equation, and reading it from left to right, zinc metal reacts with aqueous copper 2 nitrate to form copper metal and aqueous zinc nitrate. You can see that this is a single displacement reaction in which the zinc is replacing the copper. The reaction can be done as follows. If you take a piece of zinc metal plate and immerse it in a solution of copper 2 nitrate, which is blue because of the presence of the copper 2 ion in solution, letting those reactants sit for 10 minutes or so, you'll notice the solution becoming colorless and also a brownish residue forming on the metal plate. That brownish residue is the formation of copper metal on top of the zinc plate, and the reason it's becoming colorless is because those copper 2 ions in solution are coming out of solution to form the metal on the plate. And those copper plus 2 ions are being replaced by the zinc plus 2 ions in solution. Now we can see that this is a redox reaction by focusing in on the particles involved in the reaction. The zinc metal is composed of zinc atoms. These are not zinc ions on the metal plate. This is a neutral element, so these are neutral zinc atoms. The copper, on the other hand, starts off as copper plus 2 ions because copper is part of an ionic compound. So zinc atoms and copper ions are what you start with, but what you end up with are zinc ions in solution and copper atoms that have come out of solution. Looking at the zinc, we see that each time an atom goes into solution to form the ion, it must have lost 2 electrons because it starts off as a neutral atom, and to turn into a plus 2 ion, it must lose 2 electrons. And so the zinc is oxidized because the element that loses electrons is oxidized. Now, whenever somebody's oxidized, somebody else is reduced. And you can see that the copper plus 2 is what's reduced here, because the copper plus 2, in order to form a neutral copper atom, it must gain 2 electrons. And so the zinc atoms are oxidized and the copper ions are reduced. The author gives us a good picture of this reaction, which will help us see what's going on in a little better detail. You can see the reaction flask right here with the metal plate immersed in the solution. And in the bubble on the left, here are the reactant particles. You have your zinc metal atoms right here and the copper plus 2 ions in solution. Now each time one of these zinc atoms goes into solution to form the zinc plus 2 ion, 2 electrons are released. And those 2 electrons are quickly grabbed by a copper plus 2 ion, and when that happens, the copper plus 2 ion forms a neutral copper atom on top of the zinc, and then the zinc ends up replacing that ion in solution. So the zinc has turned into an ion, and the copper ion has turned into an atom. Now, these oxidation reduction reactions can be examined separately. The two processes can be described by what are called half reactions. And what a half reaction is it's like a partial chemical equation. It's a part of a chemical equation. So if you just focus in on the particle that's being oxidized, it's the zinc. Zinc atoms turn into zinc plus 2 ions. And each time one of them turns into a plus 2 ion, it must release 2 electrons. So there they are. And you write the electrons in the half reaction. Notice that the zinc atom, its charge is increasing from 0 to plus 2. That's oxidation when charge increases. Now, looking at the copper ions that are in solution, each time one of those ions forms an atom, it had to grab 2 electrons. So the copper plus 2 ions gain 2 electrons to form the atom. And here you can see going from plus 2 down to neutral, the charge decreases, and that's reduction. Now, this chemical reaction can actually be used to form a zinc-copper battery, which generates electricity. Batteries are basically chemical ways to produce electricity. And if you want to see what a zinc-copper battery looks like, I have the following diagram. Let me move myself up here. There we go. Now, the way a battery works is rather clever. The oxidation process is separated from the reduction process. In doing that, the electrons that are transferred are forced to travel along a wire to get to the other side. And that's where you can take advantage of the electricity produced. So on the left, you have zinc metal in contact with zinc nitrate in solution. So you have the zinc atoms in contact with zinc plus 2 ions. And on the right, you have copper metal in contact with copper plus 2 ions in the form of copper 2 nitrate. So it's kind of similar situation on both sides, you know, the metal in contact with its ion. Now, these metal plates are connected with a metal wire, which is where the electrons will travel along. And this part right here is called the salt bridge. We'll explain what the salt bridge does in a moment. What happens is every time one of these zinc atoms goes into solution to form the zinc plus 2 ion, we can see what's going on right here. If you have a zinc atom, say that one right there, and it goes into solution to form the zinc plus 2 ions, those 2 electrons that are released are going to be grabbed by a copper plus 2 ion. Now the copper plus 2 ions are over here, and they somehow sense through the metal that there are electrons being produced somewhere. And what happens is those electrons travel along the metal, and that copper plus 2 ion over here, and we'll zoom in on that side, that copper plus 2 ion will grab 2 electrons, and when that happens, it forms an atom over on this side. What you end up with is you end up with copper ions coming out of solution to form copper atoms. So this metal plate is getting heavier because you're gaining more copper, you're pulling the copper out of solution, and that metal plate is getting lighter because the zinc is leaving the plate and going into solution. Now, the reason you need the salt bridge is because if you're gaining more zinc plus 2 ions in solution, the solution becomes more positive. If you're getting more cations going into solution, the solution gets more positive. And so this salt bridge, which contains some inert material which doesn't disrupt the chemical reaction or interfere with it, it will release anions to balance the cations that are being released. And over there on the other side, if you're losing copper plus 2 cations, because they're forming the atoms, so you're losing cations on this side, you're getting less positive, so it's being replaced by potassium cations. And so the salt bridge kind of maintains neutral solutions on both sides, and you can think of it as kind of closing the circuit, if you will. Now, just as this reaction can generate electricity, the battery actually, which you can build from this, you can make this in the lab and you can measure the voltage. It's about 1 to 1.5 volts that you can get out of this system. The battery that you can make from this is rather crude, but other batteries take advantage of other redox reactions, and some of them are very useful. In fact, the next example that we look at shows a very useful type of battery. Before we look at this example, let's take a quick look at a few other examples of redox reactions, just to get a little bit more familiar with them. Here's figure 5.4, and in this figure, we're shown several oxidation half reactions and several reduction half reactions. For example, one of the half reactions that you might see in a redox reaction is sodium atoms being oxidized to sodium plus 1 ions. And each time an atom gets oxidized, it goes up in charge to that plus 1 ion, it must release 1 electron. Another example is magnesium can be oxidized to magnesium plus 2, releasing 2 electrons. It's not always involving a metal. You can have chloride anions being reduced, and if you have 2 chloride anions, then if they release 2 electrons, then what you're left with is 2 chlorine atoms, and those latch on together to form a Cl2 molecule. So here's an oxidation. You're going from negative, ion up to neutral molecule. Okay, that's oxidation, going up in charge. And a couple of reduction half reactions that you might see. You can see the opposite of that chlorine right there. So if you have a chlorine molecule grabbing 2 electrons, these 2 electrons can break that apart and form 2 chloride minus anions. And here you have the neutral molecule being reduced down to negative anions. Another example is silver cation grabbing an electron, and that makes it form the neutral atom. Now, this reduction half reaction we'll see in our next example on the notes. So let's go back to the notes now. In the following reaction, identify the species that is oxidized, the species that is reduced, the oxidizing agent, the reducing agent, and also write the 2 half reactions. So a lot of stuff here that you're asked to do. Now here is the chemical equation. So you start with neutral zinc, so that's zinc metal, and you react that with silver oxide, this is an ionic compound, and that forms silver metal and zinc oxide. Now this chemical reaction right here is used to form silver oxide button batteries, which are used in various medical devices like insulin pumps. So I'll show you an insulin pump here. Perhaps you recognize batteries that look like this. These are called little button batteries, and they can power various electronic devices. In fact, they're used to power insulin pumps. So here's an insulin pump that injects insulin into the body. So what it does is it monitors the glucose readings from some nearby transmitter, and it tells the pump when to inject more insulin. So as you eat foods, your insulin levels go up and down, and if you have type 1 diabetes, your body doesn't regulate its insulin as it should, and so this pump can help your body maintain proper insulin levels. Now, in this reaction, we can figure out who's oxidized and who's reduced by first labeling all the charges. In the neutral zinc metal, its charge is simply 0. Okay? And then in the ionic compound, silver oxide, the silver is in the form of +1 ions, and the oxygen is in the form of -2 anions. So I'll remind you that oxygen always likes to form -2 anions. Oxygen's in the -2 column. So when you see an ionic compound, metal and nonmetal, the oxygen's going to be -2 anions. Now the silver is down here, and you might think silver forms more than one type of ion, but if you check that second periodic table, that figure 3.3, silver actually tends to form +1 ions. Okay, that's the type of ion silver is. And so you can see it takes 2 of these silver +1s to balance the -2 oxygen. Now on the product side, we have silver metal, and that is neutral, and the zinc oxide is now the ionic compound, and so the oxygen is still -2, and therefore the zinc must be +2. So zinc in that periodic table tends to form +2 ions. Now that we have all of the charges indicated, we can clearly see who's oxidized. Just look for anyone's charge who's increasing. And if you look at zinc, it starts off as neutral, and it's oxidized to zinc +2, right there. So this is oxidized. And if someone's oxidized, someone else must be reduced, and that's the silver ions. So the silver +1 is reduced down to silver neutral. So zinc is oxidized and silver plus is reduced. So those are the species. Now what about the oxidizing agent and reducing agent? The agents are kind of opposite. And I forgot to mention this in the previous example. Perhaps you saw that on the notes. But the oxidizing agent contains the species that is reduced, and the reducing agent contains the species that is oxidized. So it's kind of weird how it's backwards. So if zinc is oxidized, we call that the reducing agent, because since it's oxidized, it kind of causes the other one to be reduced. That's why we call it the reducing agent. And the oxidizing agent contains that which is reduced. Okay, it's the whole substance which has the species that's reduced. So since silver +1 is reduced, we call this the oxidizing agent. The oxidizing agent is the substance containing that which is reduced. And the reducing agent is the substance containing that which is oxidized. Okay, so kind of backwards there. If you go back to that previous example, the zinc was oxidized, so we call this the reducing agent, and the copper +2 was reduced, so we call that whole substance the oxidizing agent. So there we go, we're almost there. And the final step is to write the two half reactions. So if zinc is oxidized to zinc +2, we can write that as follows. Zinc turns into zinc +2, and each time that happens, 2 electrons are released. And so in the reduction half reaction, we need to show what happens to those two electrons. And you can see that in this ionic compound, there are two silver plus cations, and they form two silver atoms. And so we need to show what happens to both of them. Those two silver plus cations grab onto both of those electrons and therefore form two silver atoms. So those are the oxidation and reduction half reactions. Now, before we close up this video, there's one more class of redox reactions that I wanted to look at. And these are the organic redox reactions. Now, the electron transfer in these redox reactions is less obvious than in the examples we just looked at, but as we take a closer look, you'll see what's going on. These redox reactions usually involve oxygen and hydrogen bonded to carbon. The oxidation results in the gain of oxygen or loss of hydrogen, possibly by carbon. It doesn't have to be a carbon atom, but it often is. And so what we mean by this is carbon is oxidized if it gains oxygens around it, or if it loses hydrogens around it. If either of these happen, or if both happen, then carbon would be oxidized. Reduction is the opposite. This results in the loss of oxygen or gain of hydrogen, again, possibly by carbon. As an example, let's look at the following reaction. This is the combustion of methane. And we've seen this reaction before. Here's the chemical equation. Methane gas reacts with oxygen gas to produce water and carbon dioxide. Now, before we examine the Lewis structures to see the actual electron transfer going on, let's just go back to this little definition of oxygen and reduction to see who's oxidized and reduced here. Oxidation results in the gain of oxygen or loss of hydrogen. So is anybody losing hydrogen and or gaining oxygen? Well, yeah, look, carbon starts off with 4 hydrogens attached, but now it ends up with 2 oxygens attached. So the carbon has lost hydrogen and it's gained oxygen. So we say carbon was oxidized. So this carbon is oxidized here. Okay, the carbon's oxidized. Now reduction results in the loss of oxygen or gain of hydrogen. Okay, does anyone lose oxygen or gain hydrogen? Well, looking at the oxygen, we see that the oxygen, at least looking at what happens to it once it gets into the water, here in the water it has gained hydrogen. And so the oxygen atoms are being reduced here, okay, because they're gaining hydrogen. So that's the reduction here. Now let's look at the Lewis structures of all of these molecules. Methane is carbon single bonded to the 4 hydrogens. And we'll talk about these bond dipoles here in a moment, but let's just look at the other ones first. Here's an oxygen molecule, a water molecule, and a carbon dioxide molecule. Now hopefully you remember what these Lewis structures look like. Okay, let's examine these bond dipoles. Now carbon is slightly more electronegative than hydrogen, and whereas in last chapter we were classifying a carbon-hydrogen bond as nonpolar, here we're going to acknowledge that it does have a slight greater electronegativity than hydrogen. If you go back to table 4.4, you'll see that carbon's electronegativity is 2.5 and hydrogen's is 2.1. Now the difference is only 0.4 between them, and technically that's classified as a nonpolar bond, but it's at the higher end of the nonpolar bond range. It's almost polar. And so if you had to make a choice between carbon and hydrogen, which side of the bond are these electrons closer to? Well, they're slightly pulled closer to the carbon. And carbon's doing that to all of the single bonds here. So the carbon in the center is slightly pulling the electrons away from the hydrogen. We say that there is a little bit extra electron density on the carbon in the methane molecule. Now, what about the oxygen here? Here you got, two oxygens on both sides of the double bond. There's no reason for one to pull the electrons away from the other one. And so the oxygen atoms here are both neutral. Now, what about the water molecule? What's going on here? Well, the oxygen is much more electronegative than the hydrogen. And if you go back to that table, oxygen's electronegativity is 3.5, and that's much greater than hydrogen's at 2.1. So very polar bond in the water molecule. And this oxygen is pulling electrons away from that hydrogen. It's pulling electrons away from that hydrogen. So there's extra electron density on the oxygen. It pulls electrons from the hydrogen. Okay. And then finally, let's look at what's going on in the CO2 molecule. Now here you got carbon connected to oxygens on both sides. Now the oxygens are more electronegative than the carbon. Okay, it's a difference of 1, so that's a substantial difference. And the one oxygen pulls electrons this way, the other oxygen pulls electrons that way. And while the molecule itself might be nonpolar because the bond dipoles cancel off, we can't say there's a negative side and a positive side. They're both pulling electrons away from the carbon. You see, the electrons on the carbon are pulled away by the oxygen, so carbon kind of has a lack of electrons here in this environment, and the oxygens have extra electrons, because it gets to pull them away from the carbon. So now, let's go back and compare what carbon was like in the reactants versus what it's like in the products. In the reactant side, carbon has a slightly extra electron density, and in the product side, it's missing electron density. So, carbon's kind of lost some of its electron density, and that's oxidation. Losing electrons is oxidation. And then looking at the oxygens, they start off as neutral, but here and there, they have extra electron density because they're pulling the electrons away from the atoms that they're bonded to in both cases. And so oxygens have extra electron density here. And so the oxygen has gone from neutral to gaining electrons, and so the oxygen is reduced. Okay, we don't have to write the two half reactions here to see that carbon's oxidized and the oxygen's reduced. Now, one more example in this lecture. Let's look at the oxidation of ethylene by hydrogen peroxide. Now, ethylene has the formula C2H4, and hydrogen peroxide is H2O2. And as we just did in the previous example, let's draw the Lewis structures. So ethylene has the following Lewis structure right here. Here's hydrogen peroxide's Lewis structure. And here's ethylene glycol's Lewis structure. This is the product, ethylene glycol. So I'm drawing its three-dimensional Lewis structure. Now, looking at the carbon atoms, you can see that going from its initial environment to its final environment, these carbon atoms have gained an oxygen, okay? And when you gain oxygens, that's oxidation, okay? So carbon has gained oxygens around it. This one has one next to it, and this one's bonded to one too. So these carbons are oxidized according to that definition above. All right. So if somebody's oxidized, somebody else must be reduced. Now, the reduction is the oxygen again. So hydrogen peroxide, you've probably heard somewhere that this substance, causes oxidation, or maybe it's involved with free radicals. This substance, is good at killing bacteria. And the way this works is the oxygen-oxygen single bond. This is a rather weak bond, and it's pretty easily cleaved, meaning split in two, with the electrons going back to both oxygens. It does this rather easily. If you just heat this substance up a little bit, it kind of cleaves in two, and you end up with these two particles, and these are both free radicals. These are called hydroxyl radicals, and they are very reactive particles because of the single electrons on them. Okay, free radicals are very reactive, and they will react with many other substances. And what they do is they look for substances who have weak bonds in them that they can disrupt. And ethylene has a double bond, and double bonds are weaker than many single bonds. And so what happens is these free radicals will attack that double bond right here, and you have one of these free radicals latching onto one carbon and the other free radical latching onto the other carbon. So what happens is this double bond, kind of one of those double bonds, splits apart. Okay, and one of the electrons pairs up with this one, and the other electron from the double bond pairs up with that one, and you end up with that molecule right here. All right, now looking at the Lewis structures, okay, so carbon, is oxidized because it gains oxygen atoms around it. But look at its initial environment versus its final environment. Here, in the initial part of things, we have carbon bonded to two hydrogens and another carbon. And here, in the final product, we have carbon bonded to two hydrogens, a carbon, and also an oxygen. Now, this oxygen is pulling electrons away from the carbon, okay? So carbon now has these electrons being pulled away from it. So it goes from one situation to having electrons pulled away from it. So carbon's kind of losing electrons here. It's being oxidized again because now it's connected to oxygen. Anytime you gain oxygen atoms around you, they're pulling electrons away from you. And so that's oxidation. Oxygen's very electronegative. And here you have the oxygen. Oxygen is connected to hydrogen and also another oxygen, but look at the oxygen in the product side. It's connected to hydrogen, but now a carbon, okay? So here, oxygen isn't able to pull these electrons away from the other oxygen, okay, but it is able to pull the electrons away from carbon. And so oxygen kind of gains electrons as it turns into the product. So oxygen is reduced here. So free radicals are often involved in oxidation reduction reactions, and hydrogen peroxide is a popular source of free radicals. Now, you've seen hydrogen peroxide at work in medicine. So let me show you that picture in your textbook. So here it is. You have hydrogen peroxide. This is a hydrogen peroxide water solution. And you pour that on a cut and you get all these bubbles that form. Now what's happening here is the hydrogen peroxide, which is a good source of these hydroxyl free radicals. These hydroxyl free radicals like to attack weak bonds, and they find a lot of weak bonds in the cell walls of bacteria cells. And if you have a fresh cut, you got bacteria growing, so these hydrogen peroxide The free radicals start attacking the cell walls of those bacteria, and they start killing those cells, and that's why people use hydrogen peroxide. Now, you don't want to use too much of it. You just kind of use it once as a wound cleaner, but then after that you dress your wound differently. So you don't want to keep on adding hydrogen peroxide, because then you start killing some of the good cells too. So that about does it for this lecture right here. We looked at oxidation reduction reactions. The first two examples involve metals, and the last two examples are organic redox reactions. In our next lecture, we will get into the mathematical portion of chemical reactions involving molar mass. So stay tuned for that. Aloha.